So from non-glaciated uplands, we'll move to like cold regions and sort of like think about like glacial valley that's deglaciating. And this was a large group, and they patched together a bunch of processes that are in sort of paraglacial sedimentation domain.
All right, thank you, Irina. And thank you all for your attention. My name's Ari Kopel. Are we just doing a double check on everything? Okay, great. So our group put together this lab-style notebook that asks the question, what happens in a landscape when you take away the glacier? Specifically, we're interested in a few different things. What happens in terms of surface morphology, sediment flux, ecological changes, and also what can we expect for downstream hazards. So we kind of envisioned this relatively simple system modeled after a place like the Kvíárjökull system in South Iceland with well-defined moraines, with subsurface ice that's been observed there, and with this well-defined outflow channel. And we've used LandLab components to model each of these things first on their own, and then we'll walk you through how we've coupled them together. And at this point, I want to pass it off to our compiler extraordinaire who was working tirelessly last night to make sure everything was running. Viet Bui.
Thank you so much. So we have like an example of real case situations where the topography is very noisy, but because we want to create like a playground to see what changes for moraines, especially, so I create a whole object for synthetic moraines, including like separate layer of elevations, ice, bedrocks, and thin soil. And the whole reason of this is because I want to build something that every time I run it, I modify the topography and I can always reset it to the initial state and then continue using the same object that I declare at the beginnings. So here, it's like very simple math to build up like this ice thickness. I built it from using sine functions and then some linear diffusions. Also, on top of the eye thickness, they're going to be soil thickness. It's going to be around 5 meters from all of the paper that we have going through. That is like the average soil thickness required. And then also we assume a bedrock layer. This is the combination of ice layer and a very linear slope. And then everything add together to create a topography.
Awesome. Thank you, Viet. And following having this beautiful topography to work on, we wanted to start changing things and making sediment move around. But before actually moving the sediment, we wanted to figure out what we're doing with this ice inside the moraines. So we created a class function to thaw out this ice and pulling some estimates from papers of ablation rates as a function of overlying soil thickness. We created a function to define the thaw and ablation rate of that ice as a function of overlying soil, where at low soil thicknesses, it's a constant high value. At intermediate soil thicknesses, it's a linear function, and then above a certain soil thickness, it doesn't actually thaw at all. So we walk students through plotting out, comparing the initial ice thickness to trying to run this function and thawing it, and noticing that no actual thawing occurs after this time step because the initial soil thickness in that synthetic topography is too high. So then we go in, change the soil thickness, begin to slowly melt out the ice. At small time steps, this is difficult to see, but running it over more time steps, we can see the ice is retreating and thinning at the same time. And we can do this again over 10 years of thin soil thickness. The ice has almost disappeared really quickly. So on a geomorphic timescale, this will be very sudden, but it's only going to be triggered by changes in soil thickness. And we can see even after just 10 years, this is drastically reducing that initial topography of the moraines. Moving on to how we actually move around soils, we added in a simple depth-dependent diffusion model from LandLab and walk students through what it does, how it moves sediment from areas of high elevation to low elevation, accumulating at the base and flattening out topography. And after moving around some of these soils, I'll pass it to Karen to talk about how water moves through this landscape.
Yeah, so we also wanted to incorporate some sort of representation of meltwater coming off of the glacier. And so we used the overland flow component to set up an external discharge coming into the system. We have a row of nodes up at the upslope side of the map, and those get assigned a discharge based on the hydrograph and annual average discharge from a proglacial stream in Iceland. So the discharge increases annually. You can play around with the width of the inlet as well as the initial discharge. And then that will contribute to how sediment moves around in the landscape.
Thank you. So yeah, we wanted to not only incorporate sediment movement by diffusion like Lucille told us about, but we wanted to include erosion happening from that water that Karen routed through the system. So we used space to do this, and we set some boundaries so it was only flowing to the inside of between the two moraines. And then we also wanted to account for the fact that these glacial landscapes have really high sediment supplies. And we didn't have time to mess around with actual mass wasting components. So instead, we made these parabolic piles of sediment to simulate the effects of mass wasting off of the moraine faces and the till coming out of the downslope end of the glacier. And we made a we made a component where you just plop in one of those piles of sediment at every time step in a random location between the two moraines. So I'll pass it to Tom to talk about vegetation.
Yeah, so the final component was essentially to add a vegetation component to this. Essentially, we were trying to simulate how vegetation would propagate up slope as the glacier retreats. Essentially, it's lower slopes are more likely to have vegetation than higher slopes, and we would try and make sure that there is nothing going too much into the channel itself. Have we got the knowledge report? Yeah, so as you can see, as time progresses, most of the vegetation initially goes up the channel, like avoiding the actual water channels themselves, while the moraine slopes themselves slowly sort of diffuse and eventually get some vegetation on them as well. The only other aspect of this is that the vegetated slopes also correspond with a sort of lower sort of erosion rate. So just to try and change the way that the diffusion works in the model as a whole. So yeah, that's basically it, and we'll basically pass over back to Viet to see how this all came together.
So everyone in the group have been like working tirelessly on each of the component and then running it on a very static topography that I generated. So the next part is I try to ensembling every one component into together and see how that's gonna turn out. So instead of talking more, I think we can keep showing. So you know what? So I think the time step is pretty fast because we set it to be at least 200 year for the entire period. And each time we run for like DT of 1. So in order to like save memories for the Jupyter Notebook, I actually only save each of the images or like the ensemble images into an animations class every 10 steps. So I know it's pretty fast, but we can pick up how each of the channeling coming from the moraine. And so this is for synthetic model, and we can move on to
So that's not all. So we ran everything on this very simple synthetic system, and then why not stop there? Why not actually use the topography from this real system that doesn't look so dissimilar from that synthetic system? So if you scroll down, you'll see first just illustrations of the topography. We define where the ice is. You can keep going down, Lucille, and keep going, keep going, keep going. And we eventually get to the output from this system, which hit that there, which unfortunately wasn't numerically stable. So there's a lot of work still to be done. Of course, when you couple things together, they don't always work as planned. If you have advice for how these systems that we've talked about today interact with one another and how we could make this actually work into something we could use to understand maybe this specific system, that could actually be something really interesting. So thank you to the CSDMS coordinators and ESPIn coordinators. This has been a really great week. From all of us, a heartfelt thank you.
That was an amazing compilation of like all these processes, and kudos for like getting it all together to work together for the Valley. Great, thank you.